Hello students of science. In this video we're going to talk about changes of state, how things move between solid, liquid, and gas. So first we need to define what we're talking about. A phase or state is any part of a system that has the same composition and properties. The main three that we're going to be talking about are solid, liquid, and gas. I'm going to be focusing mostly on water here because it's what everyone is most familiar with. Now when we're saying that they have the same composition, pretty much all of the ice is going to have the same composition in frozen water. Same thing with liquid. Liquid water is liquid water. Throughout the entire amount of liquid water, it's going to have pretty much the same composition. Same thing with water vapor or gas. It's going to have pretty much the same composition and pretty much the same properties. So we're going to be dividing things into two main types of transition: endothermic or heat absorbing phase transitions, and exothermic or things that give off heat. When you are putting this in your notes, I recommend that you use two colors. I'm going to use red and blue for endothermic. It's something that absorbs heat. It's going to be taking it in, and exothermic, something that actually is giving off heat. So the solid to liquid transition is melting. That of course takes in heat to melt that solid ice into liquid water. Then we've got evaporation, which is going to be a liquid to gas transition. Now the exact opposite are going to be exothermic ones, things that actually give off heat as they go through their transition. Gas to liquid is going to be condensation, and liquid to solid is going to be freezing. So I'd recommend you color those two in a different color than our endothermic ones. I'm using blue here. Now, the solid to gas transition isn't quite as familiar to a lot of people. That's called sublimation. It goes directly from solid to gas, completely bypassing the liquid state here. I'll show an example of how that works, and we'll talk about phase diagrams later to show when that happens. It doesn't happen all the time. Gas to solid is going to be kind of the exact opposite of that. That is called deposition, another exothermic reaction, something that's giving off heat as it goes straight from gas to solid, completely skipping liquid. So if we have a sealed container of volatile liquid, and water is volatile, this means that it will go from the liquid to the gas state readily. Some molecules at the surface are going to have enough energy to evaporate and become a gas. So here's a bunch of water, and we're zooming in there. Some of them will get enough energy, will actually leave the liquid state here and go straight into the gas phase. You may see this if you leave a water bottle sitting out. You're going to see it more if it's a hotter day, but at pretty much every temperature, you are going to see water leave the liquid and then condense back on the inside of the bottle there. You'll notice here, water is leaving the liquid and now it's floating around in the gas, and you'll notice the water level actually went down because now some of that water is floating around in the gas, or it's condensed on the side of the bottle. Some of those gas molecules will actually lose energy and will condense back into being a liquid. So they're going to go up, and then some of them are going to come down, and when we're going to get the evaporation rate the same as the condensation rate, we've reached what we call equilibrium. So there's always going to be stuff still leaving the liquid and going into the gas. And there's always going to be some gas leaving the air and going back into the liquid. But when those two rates are the same, we'd say we've reached equilibrium. Still plenty of movement, but it's about the same amount. It's like if you have a room of people that are exiting and people are going to be entering through a different door. When they've reached the same rate that they're going to be entering and leaving, we call that equilibrium. Here we start off with a liquid in a sealed chamber. We first have the vaporization, where pretty much everything is going to be leaving the liquid there, going into the gas. Nothing's coming back into the liquid because there's nothing in the air yet. Here we have the vaporization rate, stuff going up, marked in red, is going to be greater than the condensation rate, stuff coming down in the blue. So they're still going up. You'll notice that the water level has dropped, and then now we've reached equilibrium, where the amount that are going into the air is going to be equal to the amount coming back down. This is when you see that water bottle with all the drops of water on the inside coating it. There it's reached equilibrium. Stuff is going back in at the same rate stuff is going back out. Now we need to talk about a concept called vapor pressure. The pressure exerted by the vapor in equilibrium with its liquid is called the equilibrium vapor pressure of the liquid at that specific temperature. Now, this is kind of confusing, but think about it this way. It's the pressure that the liquid is pushing to get its liquid into the gas state. The higher that temperature is, the harder it's going to be pushing. And you'll notice that at 100 degrees Celsius, which is where water is going to be boiling, that vapor pressure is going to be much higher. You're going to see a lot more stuff exiting the liquid going into the gas at 100 degrees than you would at something like room temperature, 25 degrees down here. Volatile liquids, liquids that evaporate easy, have high vapor pressures. This whole curve is going to be shifted to the left. If you've ever put rubbing alcohol in your hand, you'll notice that it cools off very quickly and evaporates very readily. This whole curve here would be pushed to the left. They have high vapor pressures. They're pushing very hard to get stuff into the gas state. So here we have the liquid starting to evaporate, and then down here we have a constant liquid level where it's going to be entering and leaving at the same rate. A volatile liquid will reach this much quicker, and there will be a lot more in the gas state. If we have a liquid with a strong force of attraction, like water for example, it is not going to evaporate easily. It is non-volatile compared to some others, and it has a low vapor pressure. This is where we get into the concept of boiling. Boiling, of course, is the liquid to gas transition. The boiling point is the temperature where the vapor pressure is equal to the atmospheric pressure. So remember that liquid is always going to be pushing its molecules into the air, and the air is going to be pushing back down on them. When those two equal out, we would say that that liquid is at its boiling point there. So here, liquid is exiting, going into the air. Here, the air is going to be pushing back down. If you lower that atmospheric pressure, you're going to lower the boiling point. I'll show an example here. Here we have the vapor pressure curve for 4 different liquids: propanone, ethanol, water, and ethanoic acid. Now, we need to compare it to 101.3 kilopascals, which is the atmospheric pressure. So that's that red line that's going across here. Where this vapor pressure curve crosses that is the boiling point. So propanone, also known as acetone, has a boiling point of 56 degrees. That is the temperature at which, at atmospheric pressure, it's going to cross that. Ethanol is going to boil at 78 degrees Celsius. Water, of course, 100 degrees Celsius. And ethanoic acid, also known as vinegar, is 118 degrees Celsius. Now, where you get into this is the concept of boiling point is a flexible number. If I take this atmospheric pressure and lower it, I have pushed it back a little bit more in the curve here. This means that it's going to boil at a lower temperature. If I increase the pressure, I've now pushed it to the right, I'm going to increase the temperature at which it can boil. So this is basically a measure of volatility. This one is more volatile. It goes into the air quicker than this one, which goes into the air quicker than this one, which goes into the air quicker than this one here. This is the most volatile. This is the least volatile. This one enters the air slowest. This one quickest. So you don't need to copy this down, just some examples of how this boiling point is flexible. If you lower the atmospheric pressure, let's say you ever travel to Colorado or somewhere with higher altitude, the boiling point is going to be lowered because we're going to be pushing that atmospheric pressure down. So this means that things are going to boil at a lower than normal temperature. You can also simulate this in the lab. This is something called a rotovat, or a rotational vacuum machine. Basically what it means is it's going to lower the pressure inside this chamber here, and it's going to be rotating that in there. What this means is that that liquid is going to boil at a lower temperature. This is really handy if you want to make something like evaporated milk or condensed milk. If you just tried to cook it, if you brought it up to 100 degrees Celsius, you would burn the milk. If you've ever made anything with milk in it, you know that it burns very easily. So what you do is you want to remove the water, but you don't want to have to go all the way up to 100 degrees Celsius. You essentially put a vacuum there, and it's going to boil at a much lower temperature. Water will leave without burning the stuff. Unfortunately, this also means that if you're in somewhere like Denver, cooking is going to be a lot more of a challenge. Cooking is all about the application of heat to the food. Higher altitude slows down cooking by limiting how much heat you can put into water. So a pressure cooker is the exact opposite. It increases the pressure. It means that water can reach a higher and higher temperature before it boils. By putting more heat into the food, it's going to cook faster. This is what happens when you try to cook a cake at altitude. This is someone who tried to make a carrot cake mix at 6,000 feet. Because of that lower pressure, the liquid boiled at a lower temperature, and the entire cake mix boiled over. By the way, according to the people, it still tasted fine. However, that's a huge mess to clean up there. Here we have all about the atmospheric pressure was lower, the vapor pressure pushed that stuff out, and we have it boiling at a temperature you didn't want. That's Denver for you. You have to be a little bit more careful with cooking. So there's all sorts of these different things out there to do. If you're at different altitudes, you should change the composition of things to make sure that it's not going to boil at those lower temperatures. Pressure cooker, as I mentioned, is the exact opposite. It's the sealed container that the pressure increases. There's a regulator that makes sure it doesn't explode on you, but it's all about increasing the pressure so that you can increase the temperature at which it's boiling. Normally water boils at 212 Fahrenheit. A pressure cooker will make sure it doesn't boil until 250. What this means is that cooking time is actually reduced. You can cook an entire chicken in 15 minutes as opposed to an hour.
I got it used from the Navy. You could flash fry a buffalo in 40 seconds.
40 seconds? But I want it now!
You can cook rice in 20 minutes as opposed to 50 minutes, or black beans in 15 minutes as opposed to 60. By increasing that pressure, I increase the temperature, which means the food is going to cook much quicker. Finally, melting and freezing and sublimation or deposition. The freezing or melting point is the temperature where the solid and liquid state are actually in equilibrium. They're actually going to be shifting between those two temperatures quite readily. So here's our equation. Solid plus energy equals liquid. And of course, this means that it's going back and forth. If I take my ice right here and I add energy to it, it's going to transition more toward the liquid phase. If I take my water and I take away energy from it, that's going to shift it more toward the ice phase here. At 0 degrees Celsius, it's in equilibrium and it's moving. If I add energy, I'm going to shift my equation to the right here. More energy means I'm going to get more liquid. If I remove energy, I'm going to be pushing it to the left and I'm going to have less liquid, more solid. However, under certain conditions, liquids don't exist. This is a weird concept, but you get into the sublimation and deposition here. If you take a solid plus energy, it's going to go straight to vapor. The solid to gas transition is called sublimation. In dry ice, if you leave it sitting out just at regular room temperature and room pressure, it's going to go straight from solid dry ice, which is solid carbon dioxide, to gaseous carbon dioxide. There's no liquid phase. It goes straight from solid to liquid. You can make it liquid, but you have to change the pressure. We'll get into that later. If you're doing the exact opposite, gas going back to solid, that is called deposition. You may have seen this. This is called hoarfrost, and if you're like me, you've been misspelling that in your head this entire time, where essentially we have this water vapor that's in the air, and at the right temperatures and right pressures, it's going to go straight into the solid, so you get these kind of beautiful frost patterns here. They call that hoarfrost. So that is deposition. Sublimation, solid to gas. Deposition, gas back to solid.